5. Crystal aggregation and Ostwald ripening. As crystals grow, they may aggregate with each other to form larger crystals through the process of crystal aggregation. Ostwald ripening may also occur, where larger crystals grow at the expense of smaller ones due to differences in solubility and surface energy. 6. Separation and recovery. Once the desired crystal size and purity are achieved, the crystals are separated from the mother liquor, the remaining solution, using techniques such as filtration, centrifugation, or sedimentation. The separated crystals are then washed with a suitable salt or solvent mixture to remove impurities and residual mother liquor. 7. Drying and solid-state processing. The wet crystals obtained from the separation step are typically dried to remove residual solvent and moisture. Additional solid-state processing techniques such as milling, grinding, or sieving may be employed to further refine the crystalline product. 8. Characterization and analysis. The final crystalline product is characterized using various analytical techniques such as X-ray diffraction, XRD, microscopy, spectroscopy, and thermal analysis to assess its crystal structure, purity, particle size, and other properties. 9. Product handling and storage. The purified crystals are then packaged, labeled, and stored under appropriate conditions to maintain their stability and quality until further use. Crystallization is a versatile and widely used technique for the purification, separation, and production of a wide range of solid materials, including pharmaceuticals, fine chemicals, food ingredients, and specialty materials. It offers advantages such as high purity, defined crystal structure, scalability, and cost-effectiveness compared to other separation techniques. However, the success of the crystallization process depends on careful control and optimization of various parameters to achieve the desired crystal size, shape, and purity. Applications of crystallization process. 1. Pharmaceuticals. Crystallization is used for the purification and isolation of active pharmaceutical ingredients, APIs, as well as for the preparation of drug formulations with specific crystal forms for improved bioavailability and stability. 2. Chemical industry. Crystallization is employed for the purification of chemical compounds, production of fine chemicals, and separation of isomers or enantiomers. 3. Food and beverage. In the food industry, crystallization is utilized for the production of sugar crystals, salt, chocolate, and other crystalline food products. It is also used in the production of beverages such as beer and wine. 4. Materials science. Crystallization is crucial for the production of semiconductor materials, photovoltaic cells, optical fiber, and other advanced materials with controlled crystal structures and properties. 5. Environmental applications. Crystallization is employed in wastewater treatment processes for the removal of dissolved impurities and the recovery of valuable materials from industrial effluents. 6. Biotechnology. Crystallization plays a role in the purification of proteins, enzymes, and other biomolecules in biotechnological processes such as protein crystallization for structural analysis. 7. Mining and minerals. Crystallization is used for the extraction and purification of minerals from ores and industrial solutions, as well as for the production of gemstones and other crystalline materials. Overall, crystallization is a versatile process with widespread applications across industries, offering opportunities for the production of pure, high-quality materials with tailored properties and functionalities. Factors affecting crystallization. 1. Temperature. Temperature is one of the most critical factors influencing crystallization. Generally, lowering the temperature of a solution or melt leads to a decrease in solubility, causing the excess solute to precipitate out and form crystals. Controlling the precisely can help regulate crystal size, shape, and purity. 2. Solvent choice. The choice of solvent significantly affects crystallization. Different solvents have varying solubility properties for a given solute. Selecting a solvent in which the solute is less soluble at lower temperatures facilitates efficient crystallization. Additionally, the solvent's polarity can influence crystal growth and morphology. 3. Solute concentration. The concentration of the solute in the solvent solution impacts crystallization. At higher concentrations, the solution may become supersaturated, promoting nucleation and crystal growth. Conversely, lower concentrations may result in slower crystal formation or no crystallization at all. 4. Rate of cooling or evaporation. The rate at which the solution cools or evaporates affects the crystallization process. Rapid cooling or evaporation can lead to the formation of small crystals, while slower cooling or evaporation may result in larger crystals. Controlling the cooling or evaporation rate is essential for achieving the desired crystal properties. 5. Agitation. Agitation of the solution promotes mixing and uniform distribution of the solute, preventing localized supersaturation and aiding in nucleation. However, excessive agitation can lead to the formation of smaller crystals or even amorphous precipitates. 6. Seed crystals. Introducing seed crystals into a supersaturated solution provides nucleation sites for crystal growth, facilitating the formation of larger, more uniform crystals. Seed crystals can influence crystal size, shape, and purity. 7. pH. The pH of the solution can affect the solubility of the solute and, consequently, the crystallization process. Adjusting the pH to a specific range may enhance or inhibit crystal formation, depending on the solute-solvent system. 8. Impurities. The presence of impurities in the solution can influence crystallization by altering solubility, nucleation, and crystal growth. Impurities may be incorporated into the crystal lattice, affecting crystal morphology and purity. 9. Pressure. Pressure can impact crystallization, especially in processes such as high-pressure crystallization or crystallization under vacuum. Changes in pressure alter the solubility of the solutes and affect nucleation and crystal growth rates. 10. Additives. The addition of certain additives, such as antisolvents or crystal growth inhibitors, can modify the crystallization process. Antisolvents promote supersaturation and nucleation, while inhibitors hinder crystal growth, leading to finer crystals or preventing agglomeration. Disclaimer: this channel does not promote or encourage any illegal activities, and all contents provided by this channel are meant for educational purposes only. Any copyrighted material on these slides is included as fair use for educational purposes only. It will be removed at the request of copyright owners.